we're going to now look at some more power-related proofs. We're going to ask ourselves, is it true that for any even number, to the power of any odd number is always going to be even? So let's think of some examples first. Let's take the first even number we know, 2, and let's take 2 to the power of 1, right? That's going to be 2. Great. Let's do 2 to the power of 3. That's going to be 8. 2 to the power of 5. That's going to be 2, 4, 8, 16, 32. Okay, so for 2, an even number 2, it kind of looks like any odd number is going to equal an even. Let's just try one more. Let's do 4. Let's do 4 to the power of 1. Well, that's going to be 4. Okay. 4 to the power of 3. That's going to be 4 times 4 times 4. So 16 times 4. That's going to be 64. I think, right? 32. Yes. I think so. That makes sense to me. Okay. So it's looking like for just the first 2 even numbers, the first 2 odd numbers do seem to in fact make this statement true. So let's try proving this true. This is a for all statement. We're saying for all, we'll call even numbers n and odd numbers k, right? For n, all n, k that are integers, if n is even and k is odd, then n to the power of k is even. Fantastic. I'm not going to go over the definitions of even and odd. I've made plenty of simpler proof videos where I remind and write those definitions out, so I'm just going to assume you already know those definitions. If you don't, you should check out those previous videos. All right. So let's begin writing our proof and see where we go from there. So this is a for all proof, which means we start with let. And what we do with our let is we let our let suppose p is true. Let p be true. So we say let n, k be integers such that n is even and k is odd. Then let's more concretely define what we mean by n to be even and k to be odd. N is going to equal to 2m for some m that's an integer. And k is going to equal to 2g. We'll call it g plus 1 for some g that's going to be an integer. Right? There we go. Okay. Fantastic. Next, we're going to try writing this out and see if we can get it to look like an even number. So let's do that. Let's write down n to the power of k is going to equal to 2m to the power of 2g plus 1 equals. Okay, now powers are a little harder to see, so we're going to have to use some things we remember from before. So what are we going to do? We should probably split this up. We'll remember that this can be written as, this is the same as 2m to the power of 2g multiplied by 2m to the power of 1. But I'm just not going to write that one down. Okay, fantastic. Now here you can maybe immediately, because this is this is to the power of 1, you can probably just do the following. You can say this is equal to 2 times 2m to the power of 2g times m, right? We just pulled that 2 out. And then you can probably say that this is going to be some integer. I don't like that. I worry that you might have to justify that 2m to the power of 2g is an integer. But this is probably fine. But I'm not going to do that. I want to be a little more thorough. So instead what I'm going to do is I'm going to actually split our 2m to the power of 2g again. So we're going to write this out as 2 brackets 2m squared to the power of g multiplied by 2m. Okay, this is great because the reason I didn't do to the power of g all squared is because you can't really take 2m to the power of g. We don't know what g is. We just know g is some integer. It could be any integer. So instead, I'd put the number we do know up front so we can do the following step. We're going to write down 2m squared is 4m squared. This is going to equal to 4m squared to the power of g times 2m. Okay, so this might be a little easier to argue. Should we have said maybe that this has to be to the power of any odd number? Because I'm thinking now, what if g is negative? If g is negative, this might not be true, right? Hang on, let's go on a little side logic here. I did 2 to the power of 1, but I didn't try 2 to the power of negative 1. 2 to the power of negative 1 is 1/2. And 1/2 is not, in fact, even. So this statement's actually false. Okay, that's fine. This is exactly what proof writing is about. I should have thought of this question a little better because I thought this would have been interesting. Yeah, I think next time I'll think of something else similar to this, where I'm going to think a little more about the power, but this statement is in fact false. Because halfway through writing this proof, I realized, hey, what if g is negative? Well, then you're going to get a fraction, and a fraction isn't even because even is an integer. So, got to erase all of this. And instead, we're going to write out the negation. The negation of our original statement, which I regret I've erased. Let me quickly rewrite that. Okay, so now that we've thought of an example where this isn't true, we know the statement isn't true because it's not for all nk, we've thought of some nk. So you write out the negation. The negation of a for all is going to be a there exists. So the negation is going to be there exists, and there exist nk that are integers where n is even and k is odd, but n to the power of k is not even / odd, right? So what we're going to do to prove this is false, we're going to prove the red statement is true. So how do we prove it there exists? There exists is just here's an example of why this is true, because that's all this is asking for, is that there is an example where this is true. So let's write that down. We say, for example, let n, k be integers. You might not even have to add this part in. You might just be able to straight away jump to where n is equal to 2 and k is equal to -1. Full stop. Then we want to show n to the power of k is equal to 2 to the power of -1, which is equal to 1/2. And 1/2 is, first of all, it's not an integer, so it can't be even, and it can't even be odd, so it's neither of those, actually. So actually, I shouldn't have written down odd. I was wrong in my negation. I'm sorry, I'm making so many mistakes in this video, or not really mistakes, but things you're going to do when you're writing proofs. You're going to write them and realize, oh, I should have actually thought of this. I'm just going to say not even. That's all I care about, is that this is not even. And because this is already not an integer, even has to be an integer. So this can't be even in the first place. Yeah. Let me cross that out. My marker is not doing well. Okay, you know that I'm putting a slash through the element of symbol. Let me get a different marker. We're going to say, because in this case I will show why it's not an integer, or why it's not even, actually. So I'm going to say, so 2 to the power of -1 is not even because 1 over 2 is equal to 2k, where k is equal to 1/4 here, and since k is not an integer, 1/2 cannot be even. And now we write our concluding statement. In conclusion, the negation, the red statement, is true, so the original statement, even to the power of odd is even, is false. I kind of got lazy here, but if you really want to, you can rewrite the whole statement, or just say the original statement ... is false, right? There we go. This was kind of a roller coaster, but this is exactly what is going to happen when you write proofs. You're not immediately going to know the answer like I did here.